Hello everyone. So in the previous session we have studied the theorems related to radius of convergence. Anyhow we have problems to solve based on the same concept. So first let me complete the theorems, afterwards I'll go for the problems. So next theorem is Taylor's theorem in a complex plane. So this is very important question and it is repeated more number of times, and you have to practice the statement as well. Anyhow, the statement is familiar for you as you are studied in your UG classes, but the same thing will be applicable for a complex plane, right? Where you are going to study with reference to a function f of x. Here, instead of f of x, you have f of z. Why? Because it is in a complex plane. So if f of z is an analytical function at all the points within a circle C0 and with center Z0, radius R0, then at every point Z within C0, we have to prove this statement is true. So we can rewrite the same statement as this. So you have to remember these two statements and you have to memorize the statement. Fine. Now whatever the statements we have, I'm not going to write all the statements here. Just the mathematical part I'm going to explain in this session. And the notes of the same will be forwarded in the group. You just copy that. If you are finding any difficulty to solve any of the steps, please go through the video where I have clearly explained all the steps, and rest of the wordings will be copied from the notes. Fine. Now let us consider a circle C0. Let me draw here. Fine. Let us consider a circle C0 which is at a center Z0. A circle is C0 which having center at Z0, and let R0 be the radius of this circle. Fine. And now let me define a circle Z minus Z0 is equal to R. This is what the standard equation of a circle what I have drawn. Fine. Now let me draw one more circle. This is a circle C0. Now I am going to draw one more circle, say C. Fine. For this circle, let the center be same. That is, it is concentric circle. Why? Because center is same, Z0, and radius is different. What I did is I have drawn two circles with the same center and different radius. Let R be the radius of this circle, and let the equation of this circle be of the form W minus Z0 is equal to R. Now let us consider Cauchy's integral formula. As we already done this proof, so Cauchy's integral formula I am going to write. What it says, f of z is equal to 1 divided by 2 pi I into integral over c f of w divided by w minus z into dw. Why? Because we have defined a function with reference to w, right? So let me take this as equation 1 in the standard form, where we have f of z divided by z minus z0. In place of z we have w, in place of z0 we have z. Fine. So one and the same. Now let me consider the denominator part, that is 1 divided by w minus z. I am going to rewrite this term as 1 divided by w minus z0 plus z0 minus z. In the sense I have added minus z0 and subtracted the z plus z, z0. In the sense both the terms get cancelled, you will get back the same. Now I can arrange this term as like w minus z0. I'll just take common term minus, so you will get z minus z0. If you multiply minus inside, you will get back this step. Fine. Now I can take common factor as w minus z0. I'll just take the common factor. Though w minus z0 is not there in the second term, I can write this as 1 minus. Whenever the term is not there, you have to divide, right? W minus z0. If you multiply this inside, you will get back the previous step. Make sure that. Fine. What I have done is I have taken w minus z0 as a common factor from this term. Even though this term is not there in the second term, you have to divide. If you multiply this inside, you will get back the previous step. Clear? Now again I can write this as 1 divided by w minus z0 into 1 minus z minus z0 divided by w minus z0 whole power of minus 1. As you already familiar with this expression, that is 1 minus, I'll just write here, 1 minus x power of minus 1 will be 1 plus x square plus so on. What is the nth term? It is x power of n divided by 1 minus x. Right? You have already done this in your first semester, right? This formula is familiar for you. Now I am going to apply the same concept for this term, so that I can write the same as 1 divided by w minus z can be written as 1 divided by w minus z0 into, I am going to expand this term, 1 plus, and remember whatever may be the theorem, while writing the steps you just write neatly so that you will not get confusion, otherwise you will get confusion. So first term will be z minus z naught divided by w minus z naught, plus second term it is x square, in the sense z minus z naught divided by w minus z naught the whole square, plus so on. Terms will be continuing. Last term will be x power of n, in the sense z minus z naught divided by w minus z naught whole power of n divided by 1 minus x, in the sense 1 minus x is z minus z naught divided by w minus z naught. So this is what we have for the nth term. Let me write one more term before this term. See here you will get power 1 x, like something like x square, x cube. So when you keep on continuing, last term will be x power of n minus 1. X is none other than z minus, I'll just write here, z minus z naught divided by w minus z naught whole power of n minus 1. So this is the previous term, and if you continue the same process, you will get the last term, that is nth term will be x power of n divided by 1 minus x. Fine. So this is the infinite series expansion. Now let me simplify this term. So what I'm going to do is I'm just multiplying 1 by w minus z naught inside. So let me write here. So we can write 1 divided by w minus z is equal to 1 divided by w minus z naught plus z minus z naught divided by, here w minus z naught into w minus z naught will become w minus z naught the whole square, plus so on. Here you will get cube, plus so on. This term will become, see here, z, I'll just write numerator as it is, z minus z naught whole power of n minus 1. Fine. Now look at the denominator. You will get w minus, I'll just write here, w minus z naught whole power of n minus 1 will be there in the denominator, right? So when you multiply w minus z naught, you will get plus 1 here. So that minus 1 plus 1 get cancelled. You will get w minus z naught whole power of n. Clear? Now this term can be written as z minus z naught whole power of n divided by w minus z naught whole power of n into, now let me simplify this term separately instead of writing there only. So I'll just do here. So what we have in the denominator, it is 1 minus z naught divided by w minus z naught. This is what we have, right? I'm going to simplify the denominator. So when you take LCM, w minus z naught, if you keep on simplifying, it will take more time to more time as well as more space. So that is why I'm simplifying here. Minus z, where minus of minus will become plus z naught divided by w minus z naught. Minus z naught plus z naught cancel. So you will get w minus z divided by w minus z naught when you simplify this term, denominator of the term, into, we are multiplying this, that is 1 divided by w minus, into 1 divided by w minus z naught. So this will be there in the denominator. So when you simplify, I'm simplifying only denominator, right? So you will get 1 divided by, look at this term, denominator is 1 divided by this term I have written here. So 1 divided by LCM. So if you take LCM, you will get w minus z naught divided by w minus z multiplied with 1 divided by w minus z naught. So this term get cancelled. You will get 1 divided by w minus z. So when you simplify this full term, you will get 1 divided by w minus z. So I'm going to write the same here. So into, denominator will become 1 divided by w minus z. Clear? So in the notes also steps will be like this only, but I am explaining each and every step in detail. So please go through this video. Now what I'm going to do is, let me multiply by f of w divided by 2 pi I in order to apply the theorem on both sides. And at the same time, instead of multiplying and writing again, at the same time I am going to integrate. Fine. Integrate over the circle C. Fine. So if you do that, you will get, I'll just multiply, for the LHS I am just multiplying 1 by 2 pi I. I am going to write w inside and divided by this term, that is w minus z. With respect to dw, I am going to integrate. Fine. Why? Because f is a function of w, so we have to integrate over the curve C with respect to dw. I'm going to do the same here. For the first term, multiply 1 by 2 pi I into f of w. Now I have multiplied for the numerator, so denominator will be w minus z naught. I'm going to integrate with respect to dw. Similarly, second term will be z minus z naught is constant. Why? Because we are integrating with respect to w, divided by 2 pi I, integral over multiplying with f of w divided by w minus z naught the whole square over the curve C into dw. Fine. So for the next term also you will be getting the same terms. Fine. So on last term, that is this term I am going to write first. So this term will become z minus z naught whole power of n plus 1 divided by 2 pi I. I am going to multiply f of w inside. So denominator will be w minus z naught whole power of n with respect to dw with respect to c. Clear? Now let me write last term as Rn, where I'll just write here where Rn is given by, when you're going to multiply 2 pi I into f of w for this term, what you're going to get? Z minus z naught power of n will be constant. You are multiplying with 2 pi I and again you are multiplying with f of w. This will be over a closed curve. Why? Because circle is a closed curve, right? F of w divided by 1 w minus z naught whole power of n, this term, into w minus z into dw. Fine. So if you do the same, I mean when you multiply f of w by 2 pi I for the last term, that is for this term, you will get this term. So instead of writing the term here, so I have replaced it with Rn, where Rn is given by this value. Clear? Now let us consider the Taylor series expansion, as you already familiar. Now let me consider. Consider f of z, Taylor series expansion. This is in terms of f of z. F of z is equal to f of z naught plus z minus z naught by 1 factorial into f dash of z naught plus z minus z naught whole square by 2 factorial into f double dash of z naught plus so on. So when you keep on expanding, what will be the last term? Z minus z naught power of n minus 1 divided by n minus 1 factorial into f power of n minus 1 of z naught plus Rn. So why I have taken Rn is, it is since in the last expansion also I have chosen the same, or else I can say what I have done is I have applied the Cauchy's theorem. Right? So this is the definition of a Cauchy's theorem. Look at the equation 1. From equation 1, if you want you can write, since all these steps are not mentioned in the notes. Now from equation 1, you can write from equation 1. If you are finding confusion, you just write like this. So from equation 1, it is clear that, so you can look at the equation 1, what we have, f of z is equal to 1 by 2 pi into integral over c f of w divided by w minus z into dw, and that is what we have here, right? So I can write this as f of z. So that is what I have written. So instead of z I have z naught. So that is why I have replaced it as the f of z naught. Here f dash, it is generalized Cauchy's formula, right? So I can write the first term as f dash of z naught. This one is with respect to second. For the, if you have one more term, you can write that as 2 plus 1. So that will be f double dash. I am just repeating once again, this represent f of z naught. This is of the generalized form of a Cauchy's formula. So z minus z naught will be constant. So this term can be written as f dash of z naught. Similarly, if you have one more term, we can write like this. Now last term can be written as, since this is constant, I am going to keep as it is. Now apply the Cauchy's generalized formula for this term. You will get this plus Rn here. So if you apply Cauchy's generalized formula, you will get this term. So if you understand that concept, you will understand this well. Fine. Now let me take this as equation 2. Now we have to prove that this Rn tending to 0. Now to prove that this Rn term tends to 0. So let me consider the expansion Rn. What is the Rn we have? It is z minus z naught power of n divided by 2 pi I into integral over the curve C f of w divided by w minus z naught power of n into w minus z. Why I am proving this is, if Rn tends to 0, remaining will be of the form of Taylor series only. So what I have done is, I have written the expansion after multiplying f of w by 2 pi and integrating by using Cauchy's theorem and Cauchy's generalized formula, something like this. Now Rn should not be there, so we have to prove Rn tending to 0. For that I have assumed the expansion Rn. Now what I am going to do is, let me take modulus on both sides of this expansion. So take modulus, so you will get Rn is equal to magnitude of z minus z naught power of n divided by 2 pi I into magnitude of integral over c f of w divided by w minus z naught power of, I'll just take magnitude inside only, so that no need to write one more step here. So power of n magnitude into magnitude of w minus z dw I have here. So magnitude of dw. Fine. So I have taken magnitude on both sides. Now since I am splitting the magnitude inside directly, so instead of that, let me write one more step so that there will not be confusion. Right now I am not applying the magnitude. So the minute when you split the magnitude, equals will become less than or equal to. So now I am going to split the magnitude for each and every term, divided by magnitude of 2 pi I. Now integral over c, magnitude over numerator divided by magnitude of w minus z naught power of n, magnitude of w minus z into magnitude of dw. Now we need to know magnitude of all these values, right? Now let me write here. We already taken the equation of circle is since z minus, these steps also I have written in a small letters just for your understanding. If you want, you can skip all the statements, so you can replace directly. And f of w is, magnitude of f of w will be equal to m, right? And w minus z naught is equal to r. This is the equation of circle that we have assumed here, right? So this value, let me take f of w as the, m, magnitude. Fine. Now z minus z naught can be replaced as r. Clearly magnitude of 2 pi I can be written as magnitude of 2 pi into magnitude of I. Since 2 pi is constant, magnitude of I will be 1. So it is 2 pi. 2 pi I will be known to us. F of w is also known to us. Now we need the value of denominator, right? How do we define this? That is w minus z is also known to us. W minus z naught is known. So let me define w minus z. How can we extract these values? So let me explain here. Since w minus z naught is equal to r, right? So I can replace this by r. We need the value of w minus z. So I can write w minus z as w minus z naught minus z minus z naught, right? If you want, I can write one more step here. So minus z naught plus z naught get cancel, you will get back the same. Now what I am going to do is, I am going to take minus as a common term, so you will get this. Right now, let me what I have done, w minus z I have arranged in this form. Let me take magnitude on both sides so that I can write w minus z naught minus z minus z naught. Now see, if you are changing the sign here, you have to change the inequality. So I'll just write this as plus magnitude of z plus z naught. Clear? So now let me take minus common once again. One w minus z naught, I am taking minus once again, so you will get z naught minus z. Fine. Now you can note that w minus z naught is capital R. Why? Because it is this equation of circle. Minus z naught is smaller. Whether it is z naught minus z or it is z minus z naught, it will be same. Why? Because it is inside the magnitude. So I can write this as r. So magnitude of w minus z will be greater than or equal to capital R minus R. So we have obtained all the values where we have, but the dw we don't know. Since we have w minus z naught is equal to r, so I can write w as equation of circle as z naught plus r into e power of I theta. Now when you differentiate, you will get dw is equal to z naught will be constant, I into r into e power of I theta d theta you will get. Now if you are going to take magnitude over this, clearly magnitude of I is 1, so you will get r as it is. E power of magnitude of e power of I theta is also 1, so you will get r into d theta. Now since we have an equation, I just repeating once again, so I can write the equation of circle as this. Now differentiating, z naught is constant, so it will become 0. Differentiating this you will get, so magnitude, when you take magnitude of I is 1, e power of I theta is also 1. Thereby magnitude of dw is r into e power of r into d theta. Now let me substitute all these values so that this equation, that is rn, will become less than or equal to z minus z naught is r, that is small r power of n. Now 2 pi I is none other than 2 pi. So all this simplification will not be there, but anyhow, just for your reference, I have written it in a small letters. You just go through the notes. Fine. Now integral over c, f of w, magnitude of f of w, what we have assumed it is capital M divided by what we have next, w minus z naught, it is capital R power of n. W minus z is capital R minus small r into dw. Dw is r into d theta. Fine. Now anyhow this is constant, I can take this outside, so I can write r power of n divided by 2 pi into m divided by r power of n into capital R minus small r. Integral over c is a circle, so I can integrate from 0 to 2 pi. Right, so I'll just integrate r into d theta now. Fine. Now let me simplify. So I can write this as r power of n divided by 2 pi into m into r power of n r minus r. Now when you are going to integrate with respect to d theta, I can write this as, let me write here. Here r is also constant, so you can take r as outside. So you will get the integration of theta here. So integration of d theta will be theta. Clear? R is constant, you can say take outside, so you will get integration of d theta. So when you integrate it, you will get theta, limits from 0 to 2 pi. So 0 to 2 pi, when you apply 2 pi minus 0 is 2 pi. So I can write this as r power of n by 2 pi into capital Mr divided by r power of n into r minus r into 2 pi. Now 2 pi get cancelled. Clear? Now let me simplify r power of n as well, or else I can rewrite this as r power of n. I'll just group this, capital R power of n into m divided, since I have written r power of n here, m divided by capital R minus small r into r. Right? So what I have obtained is radius of convergence Rn is less than or equal to this expansion. Now you can clearly note that since r power of n is in the denominator, so as n tending to infinity, this value will be goes to 0. Right? I can write r power of n tends to 0 as n tending to infinity. Right? Now, since if it is tending to infinity, equation 2, look at the equation 2 where we have written. So here is an equation 2. Right? What we have proved is Rn tending to 0 as n tending to infinity. So this term will not be there. Why? Because Rn will become 0. So equation 2 can be written as f of z is equal to f of z naught plus z minus z naught divided by 1 factorial into f of z naught plus z minus z naught whole square divided by 2 factorial into f double dash of z naught plus so on. So this term will not be there. Anyhow, last term will be there. It is n minus 1 terms. Fine. So no need to write the last term. So this is what the Taylor series expansion is. And look at the statement here. This is what we require to prove is. Clear? In between there will be nth term. No need to worry about that. So first three terms I have written clearly. So this is what the Taylor series expansion. So we can write it in a summation form as f of z is equal to f of z naught first term as it is plus n is equal to 1 to infinity f power of n of z naught divided by n factorial into z minus z naught power of n. If you keep on giving values for n, you will get this expansion. So hence the proof. Hope so it is clear. Theorem is quite lengthy, but if you practice, it will be easy for you. Once again, I am telling you all this simplification is only for your reference. If you want, you can write. Otherwise, you can skip. Anyhow, I'll just write it. I'll try to represent it in a notes just for your understanding. And please go through the notes. So this is very important theorem, Taylor's theorem. And one more important theorem is there. It is called as Laurent's theorem. This is the statement of Laurent's theorem and it is very important. It is asked in so many years. So we have to remember along with the statement. Fine. So statement is if f of z is analytical in a ring shaped region D bounded by two concentric circles C1 and C2 with center z0, but radius is given ρ1 and ρ2 such that ρ1 is greater than, that is ρ1 is a radius of larger circle and ρ2 is a radius of a smaller circle, and z is any point in a region D, then we have to prove these statements are equivalent. So you have to practice along with the statement. You have to write the statement also. The last, just to prove, state and prove Laurent's theorem. So you have to write the statement, then you have to prove. Now coming to the proof, first let me draw the circle as per the given statement. What is the given statement? We have a circle with the center z0. Right? Let me take circle C1. So ρ1 be the radius of this circle. Fine. Now let us have one more circle with the same center, but the radius is ρ2. Why? Because ρ1 is greater than ρ2. It is given in the data itself. Let me take any point z here and w be the total complex plane. Clear? W is the total circle. So that is what we have. Now let us consider a z. Z be any point which is inside the ring shaped region D. It is not exactly the circle. It is just a ring shaped region C1 and C2. Now, let us consider Cauchy's integral formula. By Cauchy's integral formula, we can write f of z is equal to 1 divided by 2 pi I into integral over c1 minus c2 f of w divided by w minus z into dw. This is one of the consequence of the Cauchy's theorem, right? Why? Because we have two curves C1 and C2. So we can write the same as, that is along two curves, that is 2 pi I into integral over C1 f of w divided by w minus z into dw minus 1 by 2 pi I into integral over c2 f of w into w minus z into dw. Fine, so let me take this as equation 1. Now let me simplify this. In order to simplify, let us consider first term in the equation 1, that is first integral we can say. So for that, for the first integral, circle will be z minus z naught will be less than w minus z naught. Right, so w is the largest circle, w is the region where we have. So let us consider for the first integral, for any point w on c1, we can write this inequality as true. So let me consider the denominator of the first integral. It is 1 divided by w minus z. So as I already done it in a Taylor series, the same procedure you have to follow. So how can we write this as w minus z naught minus z minus z naught? Just I have added minus z naught and plus z naught, and I have taken minus as a common term. As we done in a Taylor series, I am doing the same. So 1 divided by, let me take w minus z naught as a common term. So you will get 1 minus z naught divided by w minus z naught. Fine. Now as I already told you, we have to expand this by using the infinite series expansion that we already learned, that is 1 minus x power of minus 1. Further, if you have any doubt, even in the Taylor series expansion, the concept I have used is a sum of a geometric series. Right, I'll just write here. This is just for your reference. For a geometric series, sum of n terms of a geometric series is given by 1 plus t square t power of n minus 1. So this is from the geometric series formula. This is what we have. Now I can write this term as 1 divided by 1 minus, I can split this term by 1 divided by 1 minus t minus t power of n divided by 1 minus t. If you take LCM, you will get this, right? So I can write this as 1 plus t square plus so on t power of n minus 1. Now I am going to shift this term, right? Or else I am going to shift this. So I can write plus t power of n into 1 minus t is equal to 1 divided by 1 minus t. So this formula I have used in Taylor series expansion as well as in this theorem also. So I'll just show you where I have used this. Actually this is basic. I have explained there directly by hoping you already familiar with this. See here, 1 minus t power of minus 1. I have used this expansion. See here, 1 plus x square plus so on x power of n minus 1 plus t power of n by 1 minus t. Clear? If you see this video clearly, you can understand. See here, 1 plus t square plus so on t power of n minus 1 into t power of n by 1 minus t. So this is of the form 1 divided by 1 minus t. 1 divided by 1 minus t. So here it is. Denominator. Clear? For this term, 1 divided by 1 minus t. See here, for this term 1 divided by 1 minus t, I have applied this property, or else if you want you can write this also. See here, I can write this term as 1 divided by this term. So for that I have used this. Now same concept I am going to apply in Laurent's theorem as well. So here is a concept. Now what we have, this is of the form, see here, 1 by 1 divided by w minus z naught as it is. Now let me look at the second term, 1 minus z naught divided by w minus z naught. Now it is of the form 1 divided by 1 minus t. So as I said you now, 1 divided by 1 minus t will be this expansion. Right, so 1 divided by 1 minus t, I have to apply this form. So let me expand this. So I can write this as 1 divided by w minus z is equal to 1 divided by w minus z naught as it is. Now so 1 plus t in the sense z minus z naught divided by w minus z naught plus t square means z minus z naught divided by w minus z naught whole square, plus if you continue the same, last term is t power of n minus 1 in the sense z minus z naught divided by w minus z naught whole power of n minus 1 plus t power of n, that is z minus z naught divided by w minus z naught whole power of n divided by 1 minus t in the sense 1 minus z naught divided by w minus z naught. So this is as per the geometric series expansion. You have to remember this concept. Whenever you have 1 divided by 1 minus t, you can apply this concept. I have applied the same. So I have written this expansion. Now let me simplify this expansion as we done it in Taylor series also. So I am going to multiply this term inside. So you will get 1 divided by w minus z is equal to, when you multiply inside you will get 1 divided by w minus z naught plus z minus z naught divided by w minus z naught whole square plus so on. This term will become z minus z naught power of n minus 1 divided by, here w minus z naught power of n minus 1 you have. When you multiply plus 1 you will get, as I explained in our Taylor series. So this term will become n. Why? Because when you multiply plus 1 will not, plus 1 it will be added with, so the terms get cancelled. So I can write this as z minus z naught divided by w minus z naught whole power of n. Now as I simplified this term, if you want I will show you this again. So when you simplify denominator, 1 minus z naught divided by w minus z naught. This is what the denominator is, 1 divided by this term I am going to simplify here. See here, when you take LCM you will get w minus z naught minus z plus z naught divided by w minus z naught. Minus z naught plus z naught cancels. So you will get w minus z naught divided by w minus z. So when you multiply it with 1 divided by w minus z naught, these terms get cancelled. You will get 1 divided by w minus z. So into 1 divided by w minus z. Clear? The same expansion, same term, same steps I have used in Taylor series as well. You just go through that. Now let me multiply. Only the half of the theorem will changes. Rest of the things will be same. Now I am going to multiply f of w divided by 2 pi I and integrate with respect to w. Integrate with respect to w over the curve C. So that above equation, this expression will become 1 divided by 2 pi I over the curve C, f of w divided by, I am multiplying f of w divided by w minus z into dw. Just I am multiplying the term and integrating with respect to dw, which is equal to, I am doing the same for the first term. You will get 1 by 2 pi I into integral over f of w divided by w minus z naught over the curve C, over the curve C1. Why? Because we have two circles here. For the first case I am going to integrate with respect to C1. Next I will integrate with respect to C2. So dw plus second term 1 by 2 pi I, since z minus z naught is constant, z minus z naught integral over f of w divided by w minus z naught whole square dw with respect to C1 plus so on. This term can be written as z minus z naught power of n minus 1 constant multiply 2 pi I integrate f of w, denominator will be w minus z naught whole power of n over the curve C1 dw. As usual, let me take the second term as Rn, last term as Rn, as we done it in a Taylor series also, where Rn you have to write, where Rn is none other than z minus z naught whole power of n divided by 2 pi I. Why? Because we are multiplying with f of w divided by 2 pi I divided by w minus z naught whole power of n into w minus z dw over the curve C1. Here Rn is the last term of a expansion. So this is what we have. So this term I have written here and I have denoted it as Rn. If you want you can write this term here. In the next step where you can represent it in Rn, again you can write the same. So one and the same. Now let us take An as 1 divided by 2 pi I into f of w divided by w minus z naught whole power of n plus 1 into dw. Fine? Why? Because it is given in the statement of a theorem. We have to prove this. If you want you can write. Now to prove that this is true, for that I have to prove Rn will not be there. That is Rn value should tends to 0, as we done it in a Taylor series. We have to do the same. So let me prove Rn tending to 0. So let us consider this expansion. Now as I already told you, that is z minus z naught is equal to r, such that r will be in between the radius r1 and r2. I'm sorry, rho 1 and rho 2. And moreover, w minus z naught radius is rho 1. This is all from the given circle equation. Fine. Why? Because we have, it is given in the statement. This is first circle equation. This is circle which is inside the largest circle. Now we need the value of w minus z. This is we have already done in Taylor series. We are doing the same. So I can write this as w minus z naught minus z minus z naught. What I have done is I have just added minus z naught and plus z naught. I have taken a common factor. So I can write this as w minus z naught minus z minus z naught. So w minus z naught is rho 1, z minus z naught is r. So I can write w minus z as rho 1 minus r. So with this I can write this expansion by taking a magnitude, that is modulus of Rn will be less than or equal to, I'll just write one step. I'm going to split the magnitude in this step only. So magnitude of 2 pi I integral over C1 magnitude of f of w divided by magnitude of w minus z naught whole power of n into magnitude of w minus z into magnitude of dw. Fine. So as I said, you have to remember magnitude of dw will be, if you want you can calculate in a separate step, otherwise you can write d theta. So in the Taylor series expansion I have explained, right, where you have obtained dw as, I'll just show you, or else let me do here only. So you will have w as z naught plus rho 1 into e power of I theta. So when you differentiate this you will get dw as rho 1 into d theta, right? So you can replace now. So z minus z naught will be r, small r power of n, divided by magnitude of 2 pi I will be 2 pi into integral over C1, f of w will be m1. Let me take f of w for the first case as m1 and for the second case as m2. So magnitude of f of w will be m1 here. Fine. Let me write here. So denominator w minus z naught is equal to rho 1. So you will get rho 1 power of n, w minus z naught, w minus z will be rho 1 minus r. Fine. So dw, magnitude of dw is what we have, I have written here, it is rho 1 into d theta. Now since all the terms are constant, I'll just take outside. So you will get r power of n into 2 pi I, rho 1 will be comes outside, again rho 1 power of n into rho 1 minus r, again m1 is also constant, integrate theta, you will get 2 pi. See, I'll just write here, integration of t theta over 0 to 2 pi will give you 2 pi only. Theta, again from when you apply limit you will get 2 pi, so I have written it directly, so that 2 pi get cancelled. Now let me write this as, I'll just continue here. So I can write LHS as it is, magnitude of Rn will be less than or equal to, what you left with, r power of n, I'll just try to arrange the terms, divided by rho power of n into rho 1 divided by rho 1 minus r into m1. Fine. Or else I can combine this expression as rho by r by rho 1 whole power of n into m1 divided by rho 1 minus r. We can write like this, into rho 1, right, where m1 is the maximum value of a function f of w as we already chosen. Fine. Now since the radius r is less than the radius rho 1, right, whatever the radius you have taken, it is, I'll just show you the circle. See here, radius r, small r is none other than distance from the point z to z0, and it is very small compared to radius rho 1. Rho 1 is distance from center to this point, so z is less than rho 1, or else r is less than rho 1, right? Then if r is less than rho 1, meaning is that r by rho 1 power of n will be tending to 0 as n tending to infinity. I'll just repeat once again. If you choose a point z in between these two circles, let r be the radius between those two points. From center to that point will be smaller. Clearly rho 1 is greater than r. I can say r is less than rho 1. So if r is less than rho 1, as n tending to infinity, if you keep on increasing n value, this value will become 0. In the sense Rn value will become, magnitude of Rn value will become 0. So with this equation 2 becomes, where we have equation 2, let me keep this as equation 2. So with this Rn will not be there, so Rn term will be equal to 0. So this expression can be written as, equation 2 becomes 1 divided by 2 pi I, LHS I am writing, integral over C1 f of w divided by w minus z into dw will be equal to, instead of writing we have to apply Cauchy's integral formula, right? So this term will be f of z naught, right, f of z naught, and this term will be f dash of z naught, again f dash of double z naught you are going to get. Instead of that, let me replace it with a naught plus I'll write here, you just listen to me, next step you will understand. So a1 into z1 z minus z naught plus a2 into z minus z naught the whole square plus so on, an minus 1 I'm sorry, I can write like this, an minus 1 into z minus z naught whole power of n minus 1, so on. So these terms will be continuing. Now I'll just write this expansion as sum of n is equal to 0 to infinity an into z minus z naught power of n, where here now you can understand clearly, where an's represent 1 divided by 2 pi I integral over c f of w divided by w minus z naught power of n plus 1 into dw. In the sense, you can look at the equation 2 where 1 by 2 pi I f of w divided by w, when you give n is equal to 0 you will get first term, right? So I'm sorry, yeah, first term only. So if you keep on giving the values for n, that is n is equal to 0, 0 plus 1 will be 1, so you will get the first term. N is equal to 2, you will get second term. So instead of writing all these terms, I have represent these terms as ans. So that is, when you expand this, you will get the previous step. Hope so it is clear now. What I have done is, instead of writing all these functions value again, I have represented the function value in terms of ans. So where an I have clearly written this. If you substitute an in place of a naught, replace n with 0, you will get the first term of this equation. If you put n is equal to 1, you will get the second term of this equation. So I have written equation 2 in the form of summation, something like this. Clear? Now this is for the first integral. Whatever we have done, we have to do it for the second integral as well. Look at the equation 1. Whatever we have solved, it is for the first term of an integral. Now let me consider the second term and repeat the same procedure. So let me do here. Just repeating the same procedure. If you understand the first case, you can clearly do the second case also. Now whenever this is for the first integral, right? So whenever you are going to consider a second integral, the condition will be just reverse. That is, you can write z minus z naught will be greater than w minus z naught. Fine. Again, now you consider the denominator of the second term. Fine. But very important thing is, you have to remember, when you are going to consider the denominator, what we have actually 1 divided by w minus z. Since this what we say, a circle with a equation in the form of z is greater than a circle which is in terms of w, right? So here the largest value is z. Hope so you are understanding the concept. Whenever you are going to subtract a smallest value from the largest value, you will get positive. Since w is smallest now compared to z, so you will get negative. In order to avoid, I have to consider, instead of considering 1 divided by w minus z, you have to consider 1 divided by z minus w. This is important step. Remember, so let me consider 1 divided by z minus w just to avoid negative concept. So 1 divided by z minus w can be rearranged as z minus, you have to add z naught and subtract z naught. Take minus z naught as common, you will get this. Fine. Minus z naught plus z naught. I have taken minus common. Fine. Again I can write this as 1 divided by z minus z naught into 1 minus, or else I can write this as 1 divided by w minus z naught divided by z minus z naught. What I have done is, I have just taken a common factor. 1 divided by z minus z naught common. So you will get 1 here. Minus, I will divide z minus z naught. If you multiply this term inside, you will get back this step. Fine. Now let me apply the formula. Just I have told you this term. 1 divided by 1 minus t will be of this form, right? So I can write 1 divided by z minus w as, this term you have to keep as it is, that is 1 divided by z minus z naught into 1 divided by, I'm sorry, I'll just apply the formula directly. So 1 divided by 1 minus t, it is of the form 1 divided by 1 minus t, it is 1, I'll just write here 1 plus t in the sense w minus z naught divided by z minus z naught plus t square in the sense w minus z naught divided by z minus z naught whole square, plus so on. If you continue the same, last term will be t power of n minus 1 in the sense w minus z naught divided by z minus z naught whole power of n minus 1 plus t power of n w minus z naught divided by z minus z naught whole power of n divided by 1 minus t, 1 minus w minus z naught divided by z minus z naught. Just I have applied the formula. Clear? So this is as for the geometric series expansion. I have applied whatever I have done in the first case. I am trying to do it for the second case as well. Let me simplify the denominator of this term. Now 1 divided by 1 minus w minus z0 divided by z minus z0 I have. So if you take LCM, you will get z minus z0 minus w plus z0 divided by z minus z0. When you shift it to numerator, you will get this. Right? So minus z0 plus z0 cancel. You will get z minus z0 divided by z minus w. Multiply it with 1 divided by z minus z0. So the terms get cancelled. 1 divided by z minus w you will get. See, all these steps are not explained in the notes. Why? Because it is very lengthy, as it consumes more time. So I have tried to explain in the notes, in the video in depth. But anyhow, so what is the last term we have? Is w minus z0 whole power of n into z minus z0 into 1 divided by z minus w. So let me write one more step here. So I am going to take minus as a common term in the LHS. So what can I write it as? W minus z. So if you multiply minus inside, you will get the same step only. Now I am going to multiply inside 1 divided by z minus z0 plus w minus z0 divided by z minus z0 whole square. So if you multiply, you will get same kind of step. Here w minus z0 whole power of n minus 1 divided by z minus z0 whole power of n minus 1 plus 1 will give you z minus z0 whole power of n. Just now I have simplified this term. I'll just write here plus w minus z0 divided by z minus z0 whole power of n into what I have obtained. When you simplify, you will get 1 divided by z minus w. So after simplification, you will get this. Now the same procedure you have to follow. See here, in the first case what I have done, after simplification I have multiplied with f of w on divided by 2 pi I. So I am going to multiply by f of w divided by 2 pi I and integrate over the curve C2 with respect to dw. Theorem is very lengthy. If you practice well, then only you will understand. Please practice the minute when I send the notes. So when I do that, you will get minus 1 by 2 pi I integral over C f of z divided by 2 pi I. F of z divided by w. Since I have already multiplied 2 pi I here, so w minus z into dw. This is what the LHS is. Now RHS become 1 by 2 pi I into, since z minus z0 is constant, you can take it outside. So integral over the curve C2 f of w into dw. Why? Because we don't have any term associated with this. Now the second term is also as usual. Anyhow, we are interested in last two terms. So let me write this term. This term will become 1 divided by 2 pi I into z minus z0 power of n is constant. So I can write outside. So integral over f of w into w minus z0 whole power of n minus 1. Now let me take, instead of Rn, let me take this as Sn. So in the first case what I have taken, it is Rn. Let me take this as equation 2. Right? So let me take this as equation 4. Now as usual, where Sn I have to write, where Sn will be, you no need to behead this. You can just simplify as and how you are doing. So let me integrate this. Integral over C, since 1 by 2 pi I is there. So f of w, since what is the constant term? Z minus Z0. I'll just write here. Sn is equal to 1 divided by 2 pi I. Here the constant is Z minus Z0. So you can take it outside. Whole power of n. Right? Integral over C2. What is the numerator? That is f of w multiplied with w minus Z0 whole power of n minus 1. For the previous, n, right? We have n here. N divided by z minus w into dw. I'll just explain this step once again. See here, what I'm doing is just doing multiplication with f of w by 2 pi I and integrating with respect to dw. All these terms will be clear. Sn is, see here, I have just multiplied 1 by 2 pi I for the last term and have taken z minus z0 power of n outside. So what you have inside, f of w you have to multiply. Numerator is w minus z0 whole power of n. Denominator is z minus w into dw. Now as usual, we have to say prove that Sn is tending to 0. Right? So let me prove. For this term, we have to prove this is tending to, let me write, to prove that Sn tending to 0 as n tending to infinity. So let us consider the known facts. That is, we know that z minus z0 is equal to r. These are all equation of a circles. W minus z0 will be equal to rho 2. Why? Because rho 2 is less than r. Right? You can look at the circle clearly. Fine. Rho 2 is distance from here to here. R is here to here. So R2 is small compared to R. So that is why rho 2 is less than R. So all this concept, if you want, you can remember. And moreover, what else we need? Magnitude of Z minus W. So Z minus Z naught is known. F of W will be, let us take F of W as M2. Why? Because we have already chosen it as M1 in the first case. So what else we need is, this value is known, W minus Z naught value is also known, Z minus W value we need. So I can write Z minus W as magnitude of Z minus Z naught minus W minus Z naught. What I have done is, I have added minus Z naught and subtracted minus Z naught. I have taken minus as a common term. So I can write this as greater than or equal to Z minus Z naught minus W minus Z naught. So magnitude of Z minus W will be greater than or equal to Z minus Z naught values are, W minus Z naught will be rho 2. So this is what we have. Fine. Now let me consider magnitude for Sn. So you will get magnitude of Sn. I'll just apply directly. I'm going to split it directly. So I can write less than or equal to 1 divided by magnitude of 2 pi I, magnitude of Z minus Z naught power of n, integral over C, magnitude of F of W, magnitude of W minus Z naught power of n, divided by magnitude of Z minus W, magnitude of dW. As I already said, magnitude of dW will be rho 2 into d theta. Fine. Now with all these values, I am going to substitute 1 divided by 2 pi I value is 2 pi, magnitude value. Z minus Z naught is R. So you will get R power of n here, into integral over C. F of W value is, I have assumed it as M2. Fine. W minus Z naught is rho 2. Rho 2 power of n you will get, divided by Z minus W. Z minus W is R minus rho 2. Now dW is rho 2 into d theta. So with all this, let me take a constant outside and let us integrate. So RHS is LHS is Sn less than or equal to 1 by 2 pi R power of n, M2 constant, R2 power of n constant, R minus rho 2 is also constant, rho 2 constant. When you integrate theta, you will get 2 pi. Right? So 2 pi get cancels. What you left with, I can write this as R2 divided by R whole power of n, M2 divided by R minus rho 2 into rho 2. Clear? Here also the same thing, as rho 2 is less than R. Why? Because you can observe it in a what we say diagram. See here, it is a diagram. So Z is point here and R is radius from here to here. You can clearly note that R2 is very small compared to R. So R2 is small compared to R. So if this was the case, I can write R2 by R power of n tending to 0 as n tending to infinity. Meaning is, magnitude of Sn value will be equal to 0. So with this, equation 4 becomes, where I have assumed the equation 4, which is in terms of Sn. So equation 4 becomes, Sn value will be not will be there. I mean Sn value will become 0. So equation 4 becomes, how can I write? LHS is minus 1 divided by 2 pi I into integral over C, F of Z divided by W minus Z into dW. Instead of writing all the functions as we done it in a first case, let me represent it with some constant, say B1. B1 into Z minus Z naught power of minus 1. Why? Because we have Z minus Z naught in the denominator. So when you shift it to numerator, you will get minus 1. Plus B2 into Z minus Z naught whole power of minus 2. Plus so on. Right? Meaning is, I can write this term, this expansion as, I can write it in summation form, n is equal to 1 to infinity bn into Z minus Z naught power of n. Clearly, where bn is equal to 1 divided by 2 pi a into integral over C, W minus Z naught power of n minus 1 into F of W dW. Now you can clearly note that whenever you are going to give the value of n, you will get all these expansions. See here, first term is b1 into z minus z naught power of minus 1. So I have clearly mentioned here. See here, 1 divided by z minus z naught power of n minus 1. b1 is 1 divided by 2 pi I into f of w dw. Fine. So when you give n is equal to 1 here, so you will get, why? Because n is starting from 1. So when you give n is equal to 1, 1 minus 1 will become 0. So this term will not be there. So you will get f of w into dw. First term you will get. So when you give n is equal to 2, you will get the second term. When you keep on giving the values, you will get this expansion. So I can write like this. Clear? So bn is this expression. And moreover, an also I have done. So here it is. Clear? Now look at the statements. An is this expression and Bn is given by this expression. Clear? So we have obtained these two expressions, but how can we obtain this expression? So let me take somewhere I have written, see here. So let me take this equation as, say, equation A, where we have expressed a function in terms of A. I mean in terms of summation. Similarly, in the second case also we have expressed it in terms of some value B, summation value B. Here it is. So let me take this as equation B. Right? So now I'm going to substitute equation A and equation B. See here, equation A and equation B in equation 1. Here you have a equation 1. Now B and A in 1. So equation 1 is f of z is equal to, now look at the value of this expression where we have done. Equation A says that 1 by 2 pi I, see here, equation A is 1 by 2 pi I into f of w divided by w minus z into dw value is this expression. So I can write this as summation n is equal to 0 to infinity an into z minus z naught power of n minus, now minus overall this expression value I have obtained in equation B. Here is an equation B. See here, this expression value is summation n is equal to 1 to infinity. So minus of this value, anyhow we have minus already. So minus of minus will become plus bn z minus z naught power of n. And that is what, z naught power of minus n. Clear? So and that is what, why? Because here you have minus terms, I mean minus power minus 1 power minus 2, so that is how we have minus n. So hence the expression. See here, this is the given expression and an and bn values are given by here. Equation A and B gives an and bn values. Clear? Hope so it is clear. Maybe theorem looks somewhat clumsy as it is very lengthy, but I'll send you the notes in very simplified form. You just go to the notes. I have explained the steps in detail in a video. Please follow the video and practice well. Hope so it is clear. Thank you. Continue in the next session. And one more thing, whatever I have done in this session is very important. Please practice well.